Hello, welcome to CSC7132, Operating Systems and Networking. This is Brady Chen. Now in section 7.2, we're going to talk about the page replacement algorithms. Now using paging, we know that a process going to be measured using the number of pages. So a process is going to divide it into pages. Let's say this is process 1. Okay. Now in multi-programming environment, a computer operating system may support multiple processes, right? So then we have another process, which is a little bit smaller, P2, and a P3, another process. Okay, so these processes are basically fighting for the computer resources, right? So let's say we also have the physical memory. And again, using paging, the memory is also divided into page frames. Now, page size and frame size, page frame size are the same. So now memory consists of a fixed number of frames, because once you purchase a computer system, the memory size is always fixed, right? So we also mentioned that for various different reasons, there's no way you can load all the pages, okay, into the computer memory. Now, one reason is that sometimes one process contains more pages than the number of frames. The other reason is because if you support multiple processes, then the total number of pages may exist the total number of frames, right? So there's various different reasons that you cannot load all the pages into the frame. So that's the reason why we introduced the page replacement. So if one process is running, an operating system wants to load a page into the physical memory, and if there's no free frames, okay, so the memory is full, then we need to pick a victim, pick one of the pages which is currently in the memory. Okay, so we need to pick one of the pages. Now how are we going to pick the pages? That's something we're going to talk about. It depends on the page replacement algorithm we use. Okay, now suppose we pick a victim. Now what we do is, using page replacement, we're going to actually replace this page in the memory with the page that want to be running. Okay, so that's the page replacement. So now when we do the page replacement, you have various different options. So for example, if one of the page in process 1 wants to be loaded into the physical memory, okay, now are we going to replace only the other pages belongs to the same process, or we can also replace the pages belongs to any other processes, right? For example, page 0, 1, 2, 3, page 3, P3 wants to be loaded into the memory. So are we going to only replace the pages, like belongs to P1, or we can replace the pages belongs to P2 and P3? That's a good question, right? Now, one approach to sharing the frames among multiple processes is to let the process compete with one another. So that means once we set a criteria for the page replacement, it doesn't matter if a page 3 wants to replace the existing pages in the memory, the page 3 can replace a page in the memory which belongs to the other process. Okay, so that's one of the approach. Okay, so when a page fault occurs and then no free frames available, the algorithm chooses one of the resident pages from replacement or for replacement, regardless of which process the page belongs to. Okay, so that's the approach, one of the approach we're going to use. Okay, now when we talk about page replacement, we're going to introduce another concept which is called a reference string. Okay, so the reference string is a sequence of page numbers. A reference string is a sequence of page numbers referenced by the executing program during a given time intervals. Okay, so reference strings are used to compare different page replacement algorithms by counting the number of page faults generated. Okay, now let's talk about this reference string a little bit more. Why we want to use the reference strings during the page replacement. Okay, so let's talk about the page reference string and why we want to use the page reference string in page replacement algorithm. So let's assume that we have a logic memory address, which is 12-bit virtual address. Okay, so if you count, that's 3, that's 4, another 4, another 4, right? And then we're going to actually split virtual address into 4, 8. Okay, using the paging. So the first 4 bits represent the page number, and then the next 8 bits represent the offset or offset number. So we use 4 bits for the page number. Now we know that with 4 bits, how many different page numbers we can represent? 4 bits, right? So the total number of pages is going to be 2 to the 4th, which is 8. Okay, so for this virtual memory address, we only have 8 pages. Now, what's the offset? Offset represents the size of each page. So the offset is 8-bit, right? So with 8-bit, how many different numbers we can represent? It's 2 to the 8, which is 256. So that means with this paging, you have the virtual memory address contains 8 pages, and each page contains 256 logic address, right? So that means the page size is big. It contains 256 addresses. Now, let's actually say that this is the sequence of execution. Now, each one represents the virtual address. So this program going to start with virtual address 0000000 all 0. So that's the first, the instructions. That's the first memory address. Okay, the virtual memory address. So we're going to execute the instruction in this virtual address. And the next instruction will be in this address, memory address. So this first one is 0, the second one is 4, right? And then next instruction going to be we are executing located in this memory address, which is 8. And that's the next address, logic address. And then after you execute this, and then the next instruction we're going to execute locates in this memory address, logic address. Okay, so that's the order. Okay. Now logically, so this is the first instruction. The memory address, the memory address of first instruction. That's the second. That's the third. That's the fourth. That's the fifth, right? So you're gonna run this one after another. Okay. Now, the reason we introduced the page reference is because, logically, these two addresses are close to each other. So these two instructions, after you execute this instruction, you're going to execute that instruction, right? But remember, using paging, so we find out this memory address, logical virtual address, located in page 2 because the page number is 2, and these 4 are located in page 0, right? So that's why I use different color to separate these. Okay, so now the follow-up virtual address, these are all located in page 2. Okay, and then after this virtual address, then there's a jump because this address is located in page 3. Okay, and then after running the virtual address in page 3, then suddenly it jump back to page 0, right? So it's possible because when we run a loop, or sometimes when we actually call a function or subroutine, so the order of execution may changes. You don't always follow the sequence. Now, so we actually define this as the page reference string. Okay, why we want to do this? Now, because when you use the paging, so we may actually load the page 0 to one page frames in the memory, and the page 2 will be loaded into another frame, right? Now, so these frames may not be close to each other. Okay, so, or using the demand paging, so if page 0 is loaded into, for example, page 0 loaded into frame number frame 10, and the page 2 loaded into frame 100, and the page 3 probably is not loaded yet using demand paging, right? So when you execute, these virtual address, now for these 4 virtual address, it's all in page 0. So these instructions are basically close to each other because they are in the same physical memory location. At least they are very close, right? Now, when you have a jump over here, then you suddenly, the next instruction going to be in frame number 100. So there's a big jump, okay? But once you actually jump to page 2, then the next, virtual address is going to be also nearby, right? So then you're going to actually, there's another jump. So you actually execute the instruction in page 2 and to page 3. And now, because page 3 is not loaded yet, using demand page, now what happens? We're going to have a page fault, right? Now, page fault is an interrupt. Okay, we just mentioned it in the very chapter, the first module. So it's an interrupt. So then this page 3 is not loaded. So then the operating system is going to check the physical memory to see whether there's any free frames. Okay. If there's a free frame, then load the page 3 to that free frame and update the page table, update the present bit, right? Now, so let's say we find a free frame, load the page 3 into F50, the frame number 50. So page 3 is loaded to frame number 50. Now, once the page 3 is loaded into frame 50, then it's in the memory now. So for the next instruction, which is also located in the page 3. So now the page 3 is already in the physical memory. So you can actually just, check the page table and map the logic virtual memory address into the physical memory address. So there's no page fault anymore, right? Because page 3 is already in the physical memory. So basically page 3 or page fault happens only in the first time when the instruction in this page is executed. So only the first instruction in page 3 try to map to physical memory, and the operating system find out page 3 is not in the physical memory. Then there's a page fault. So page fault only happens only once. Then the follow-up instructions, they should be okay, because all these instructions belongs, are located in the same physical memory location. And then here we have another jump, right? We jump from page 3 to page 0. Now, hopefully, when you jump to page 0, hopefully we find out page 0 is in the physical memory, because page 0 is mapped to a frame number 10. Okay, hopefully that's the case. So in this case, there's no page fault, right? Okay, remember, that's the hope. Because why? It's not guaranteed. The page, we hope that there's no page fault, because page 0 is already mapped. But you never know, because maybe, the previous page fault may actually find out, okay, I want to remove the page 0 from frame number 10. So then if that's the case, that's really bad, right? So let's say now we have another situation. So I'm going to change different color so you can see what I'm talking about. Let's see. Let's say, suppose, let's say we forget about this. Now, suppose when page 3, we enter the page 3, right? And then there's a page fault. And then initially we say we find a free frames, okay, which is actually in page 50. So we actually load the page 3 into page 50. Now, suppose this is not happening, okay. Suppose we run out of physical frame. So that means the physical memory is full. Okay. So then we want to find a victim. And then we find, okay, page 0 is in physical memory, in a frame number 10, and we want to replace, page 0 with page 3. So we want to kick a page 0 out of frame number 10 and load page 3 into frame number 10. Okay. So initially, page 0 is in frame number 10, but now not anymore, because in this page fault, page 3 gonna actually will be loaded into page frame number 10. So page 0 gonna be out. Now in this case, that's really bad, because this page fault replaced, kick the page 0 out of frame number 10, and then this time we want to actually run an instruction which is located in page 0. Now we find out page 0 is not in the physical memory anymore, right? But once we kick it out, we're going to change the present bit for page 0 back to 0, so it's not in the memory anymore. So then if that's the case, then running from page 3 to page 0 is going to trigger another page fault, right? Because page 0 is not in the memory anymore. So there's another page fault. So we don't know, even though the page 0 was referenced previously. But if we try to reference the page 0 again, there's no guarantee that page 0 is still in the memory. So we may or may not, trigger the page fault. Okay, so there's another jump. So then we may have a page fault or may not, if we are lucky. So that page is actually still in the physical memory. Then we can just refer to this, using the page table, so you can do the reference. So in that case, page fault only happens when you actually jump from one page to the other. So so when you use the page replacement algorithm, the things that matters most is the page reference, right? We don't care about the actual memory, virtual memory, because if all these memory nearby are in the same page, then only the first reference may trigger the page fault. The follow-up may not, definitely not. Okay. So that's the reason why when you use the page replacement algorithm, we only care about the page reference string, okay, not the actual memory reference string, okay. So in this particular case, the page reference string is 02309, so 02309. Okay, so let's talk about the various different page replacement algorithm. Okay, so the first algorithm we're going to talk about is the optimal page replacement algorithm. Okay, when we say optimal, basically it means the best, right? Okay, so the optimal page replacement algorithm selects the page that will not be referenced for the longest time in the future. Okay. Now, before we actually talk about this, let's assume that we have a physical memory which contains 4 page frames. That's pretty small, right? And in reality, any actually physical memory will contain more than actually 4 frames. Actually, it will contain millions of frames. But for the purpose of discussion, we assume that it contains only 4 frames. Now, for the virtual memory, virtual address, it's much bigger. In this case, we have the reference string RS, which has the page number 20314. Looks like the virtual address contains pages from 0 to 4. So that means you have more pages than the friend numbers. Okay, so most likely page fault gonna happen. So the page replacement has to be used. Now, the optimal page replacement algorithm select a page that will not be referenced for the longest time in the future. Now, how does that work? Okay, let's see. Here's the reference string. Okay, now here's the timeline. Okay, so the first page we will reference is page 2. Okay, so initially, that's time 0. Initially, page 0 is mapped to friend number 0. Page 1 maps to friend number 1. Page 2 maps to friend number 2. Page 3 is located in friend number 3. So the memory is full, right? Friend 1 contains friend 0 contains page 0, friend 1 contains page 1, friend 2 contains page 2, and the friend 3 contains page 3. So it's full. Okay. So the first page the page we will reference is 2. Okay. So we check, the operating system is going to check the physical memory to see whether page 2 is in the memory, right? And we find out page 2 is in the physical memory. It's actually in the friend number 2, right? So that means there's no page fault because the page is in the physical memory. So we're going to continue with this. So we're going to copy the pages, and then after you complete all the instructions in page 2, it jumps to page 0. Okay. Now we check, is page 0 in the memory? The answer is yes, page 0 is in friend number 0. So then we use the page table and map the virtual address to the physical address. That's fine. Okay. Now page 3, yes, it's in the memory, so we don't have to change anything. Now what about page 1? Yes, page 1 is in the physical memory, right? So for the first 4 page references, there's no page fault because all these pages 2, 0, 3, 1, they are already loaded into the physical memory. And then the next page reference is page 4. Okay. Now page 4 is not in the physical memory, right? And then physical memory is full. So you have to replace one of the page. Okay. So then we're gonna add the page replacement algorithm actually kicks in and replace the page. Now, which page we should replace? Are we gonna replace page 0, page 1, page 2, or page 3? Now, using the optical page replacement algorithm, we will, we will actually select the page that will not be referenced for the longest time in the future. Okay. Are we going to replace page 1? No, because page 1 will be referenced right after this. Okay. So if we replace the page 1, then we will actually reference the page 1. So we can actually call the page 1 and we have to bring the page 1 back to the memory, right? So it's not good, based on optimal, that's not a good idea. Okay, so we're going to keep the page 1. Now, are we going to replace page 0? So page 0 will be referenced very close to that one, right? And again, page 1, page 2. Now, what's the page that will not be referenced for the longest time in the future? not 0, not 1, not 2. Okay, we have 0, 1, 2, 3, and a 3, okay, is the farthest from this page reference 4. So what we're going to do, we're going to replace the page frame number 3, right? So we replace frame number 3. Okay, so that's because the optimal page reference algorithm select a page that will not be referenced for the longest time in the future. Okay, so 1 will be referenced very quickly, 2 will be referenced, and 0 will be referenced, and 2 will be referenced, and 3 will not be referenced for the longest time. So we replace, page 3. Okay, so what's next? Next, page 1. Yes, page 1 is in the physical memory. So there's a page fault, right? And then what about page 0? So page 0 is in the frame number 0. So we don't need to change it. It's no page fault. 1, that's okay. So no page fault. 2, that's okay. It's still all in the page in the physical memory. So 1, 2, 3, 4, no page fault. And then the next one is page 3. Now page 3 is not in the physical memory, right? Now, which one we're going to replace? Using the optimal page, we're definitely not going to replace page 0 because page 0 will be referenced quickly after this, right? So we don't replace page 0. Now for page 1, 2, 3, because page 0 is the last one in the reference string, so it really doesn't matter which one we replace. Okay, so but we definitely don't replace page 0, so we keep the page 0. And these 3, I randomly pick page 1, so I replace page 1. So and keep the page 2, and keep the page 4. Okay, so there's a page fault, and then 0, 3, 2, 4, because there's no page fault. So I just copy this string. Okay, so that's the optimal page replacement algorithm. Now, optimal page replacement algorithm is actually good because if you actually check any other page replacement algorithm, we will find out optimal page replacement algorithm will result in the minimum number of page fault. Now in this case, there are only 2 page faults. Okay. Now when you compare 2 page replacement algorithm, you just compare the number of page faults. The algorithm with fewer number of page faults is better. Okay. So from this perspective, optimal page replacement algorithm is the best. That's the reason why we call it optimal. However, optimal page replacement algorithm has one, there is a actually big negative thing about optimal page replacement algorithm. Why? Because optimal page replacement requires the knowledge of future page reference. Okay. So when the operating system actually execute a process, so you're gonna execute the instruction in, each instructions are located in the virtual memory address. So typically, before you execute the instruction, you never know which address we're gonna actually reference to. So eventually, we never know which the page actually string we're gonna follow. So we don't know which page will be will be actually used after this one. So we need a future knowledge of this. So that means we need to know the page reference string during the loading time. So before we actually execute the program, we should know the page reference string. We should know the order of execution. Now, normally that's not possible. Okay, so that's why optimal page replacement is not realistic. But it provides some kind of benchmark for us. So when you actually, define any actually page replacement algorithm, and when we try to compare two different page replacement algorithms, we use the optimal page replacement algorithm as some kind of a standard. We just compare with the optimal page replacement. If the page replacement algorithm is, the performance is closer to the optimal, that's a good page replacement algorithm. Okay, so here's a summary of the optimal page replacement algorithm. So number one, the algorithm is guaranteed to generate the smallest number of page faults for any reference string. That's good. Now, why that's good? Because page faults are very costly. The page faults are going to involve the movement of the page from the physical, the disk space to the memory. Because the virtual memory, memory space is going to be actually all these information are located in the disk, not in the memory. And access the data in the disk space is much slower than access the data in the memory. Okay. However, so even though it's good, however, the algorithm is unrealizable because the replacement decisions depend on future references, which are unknown at the runtime. Okay. So, but this algorithm provides a useful lower bound on the number of page faults for comparison with other algorithms. It provides a very good benchmark. Okay. Okay, now let's talk about another page replacement algorithm. That's the Fifo. Okay. Now we already know Fifo basically means first in, first out, right? So now the Fifo page replacement algorithm selects the page that has been resident in memory for the longest time. Okay. So let's see. Again, we use the same example. We have a memory which contains 4 frames, frame 0, 1, 2, 3, 4, and the page 0 is already in frame 0, page 1 is in frame 1, page 2 is frame 2, and page 3 is in frame 3. So we also assume the page 0 is the first loaded page, okay, and then followed by page 1, page 2, page 3. So the page 0 has been resident in the memory for the longest time, and then page 1, page 2, page 3. Okay. So let's check out how this Fifo page replacement algorithm works. Okay, for the first 4 page references, we know that the page 2, 0, 3, 1, they are all in the physical memory, so there's no differences between Fifo and optimal, right? If it's already in the memory, so there's no page fault. Okay. Now things start to change, when page 4 is referenced, because page 4 is not in the physical memory. Now, using the optimal, So we check the future reference, right? And we replace the one that's farthest in the future, that's not referenced. Okay, so that's 3. Now using the FIFO, it's different because we're gonna check these pages in the memory 0, 1, 2, 3, 4, and which one has been resident in the memory for the longest time. Since 0 is the first loaded one, so that's the longest one, right? So we replace the 0. Okay. So the page 4 going to replace page 0, which is in frame number 0. And then now page 4 is the most recently loaded page, right? So in this case, we need to point to the next one. Now page 1 is the oldest page in the memory. Okay. So next one, page 1. So we find out page 1 is in the memory, right? So there's no change. So there's a page fault here, 3. So there's no page fault. And then now comes to page 0. Now 0 was in the physical memory, but now 0 was replaced by 4, right? So now we're gonna do the next replacement. So which one we're gonna replace? We're gonna replace 1, right? Because 1 is the oldest at this moment. So 4, you're going to replace 1 and 2, 3, and there's a page fault. Okay. And now the next page, the reference page is page 1. That's kind of unfortunate. That's nightmare because we immediately call page 1 right after page 1 was replaced. That's bad, right? So then we have to, so we have to actually point to the next oldest one, which is page 2. So now page 1 is referenced and it's not in the memory. So which one we're going to replace? We replace that one, page 2, right? Because page 2 now is the oldest one. So 4, 0, 1, 3. So now we move the pointer to page 3. Okay. Now right after we replaced page 2, then page 2 is referenced again. Okay. That's bad, right? So then we're going to replace 2. 2 replaced 3. And then now 4 is the oldest one, right? So now we're going to replace, page replace 3. Which one we're going to replace? Replace 4 because 4 is the oldest one. So 3, 0, 1, 2, and then the arrow going to go down to 0. And then there's no page fault, right? So that's okay. We copy it. So we have page fault here. We have page fault here. We have page fault here and no page fault. Now how many page faults we have for the FIFO? 1, 2, 3, 4, 5. We have 5 page active faults. Compare with 2 for the optimal. That's really bad, right? So that's the FIFO. Okay. Now in the diagram, we just use the pointer to point the pointer to the pointing to the oldest page in the memory. Now in reality, when you actually implement this FIFO, we can use a queue. Okay. So the queue contains, the size of the queue is the size of the memory, number of frames. Okay. So in this case, initially, the queue contains 4, and we actually say queues. That's a queue head, the head of the queue. That's the tail, the queue end. That's the tail of the queue. 0, 1, 2, 3. So it's in the opposite way. Okay. So when you replace anything, okay, So there's no page fault, so we're not going to replace anything, right? But when there's a page fault, what we're going to do is we're going to push the queue down. So we're going to push actually 1 down to replace this, push 2 down, push 3 down, and then we put the 4 at the top. So the 0, page 0 is actually out. So because we just push everything down, and at the top we replace with the new page. So the page at the header, it's always the oldest page. So that's the oldest. That's the newest. Okay. So then there's no page fault, and then there's a page fault again, right? So what are you going to do? Page 0, we're going to push down. So as 1 is out, so 2 going to be here, 3 going to be here, 4 going to be here, and then 0 going to be here. Okay, so again, there's a page fault. We're going to push down. So 2 is out. So 3 going to be here, 4 going to be here, 0 going to be here, and 1 is replaced here. Okay, again, push down 4, 0, 1, and 2. Again, push down 0, 1, 2, 3. And there's no page fault. Okay, so the queue basically is used to keep track of, make sure that the oldest one will be replaced. Okay, that's the Fifo. So let's talk about the advantage and the disadvantage of the Fifo page replacement algorithm. Now, number 1, the algorithm is easy to implement. Okay, now that's always the case in general. Okay, for process management, memory management, like a process scheduling, Fifo is always the easy one to implement. Okay, so it's just requiring only a single pointer to designate the oldest page in the memory. Okay, so we can also use the queue to do this. Now, Fifo algorithm takes advantage of the principle of locality, except for branch instruction. Okay, now if there's no branch, like a loop, while loop, or if statement. So if we actually meet the while loop, then you can actually jump to a different location. Otherwise, if you actually use like a sequential algorithms, then it's just follow the order. Fifo actually does a good job doing this. Okay. So an execution advances sequentially through the code. So the likelihood of referencing a page used in the distant past diminishes with time, and similarly, many large data structures are processed in sequential order. Now, in that case, if everything's running sequentially, the Fifo actually is pretty good. It's also very easy to implement, right? Okay, so let's introduce another page replacement algorithm, the LRU, the least recently used page replacement algorithm. Now, the LRU selects the page that has not been referenced for the longest time. Now, the LRU look at the past of the page reference, unlike the optimal, which is basically look at the future. So LRU look at the history. So that makes the LRU doable and a realistic page replacement algorithm. Now we will talk about the logics behind the LRU, but we first talk about what is LRU, how can we run the LRU. So again, we can have a physical memory which contains 4 frames, and also initially page 0 is loaded into frame 1, frame number 0, page 1 loaded to frame 1, and page 2 loaded to frame 2. Okay. So here's the reference string, right? So for the first 4 references, 2, 0, 3, 1, since these pages are already in the physical memory, so then there's no page fault, right? So we're gonna keep the pages in the physical memory. Okay, so there's no page fault. There are no page faults for the first 4 references. Now, for the 5th reference, page number 4. Now, 4 is not in the memory, so we have to replace the 4 replace one of the page using the page replacement algorithm. Using LRU, we're going to select a page that has not been referenced for the longest time. Okay, so let's take a look. Are we going to replace 1? No. 1 was just recently referenced. Not a 3, right? Not 0, but the 2. 2 has not been referenced for the longest time compared with the other pages. So we're going to replace 2. So we don't change anyone, but replace 2. So there's a page fault. And then for the next page references, reference strings 1, 0, 1, and since 1 is in the physical memory, 0 is in the physical memory, so we don't change the we don't change anything, right? And there's no page fault. No page fault. Now for the next one, page 2. Now page 2 is not in the physical memory. So using the LRU, which one we will replace? So which page we will replace? Again, let's look at the history. Page 1 was referenced recently. Page 2 was referenced. Page 0 was referenced recently. And also the page 4, right? So we don't replace page 1, don't replace page 0, don't replace page 4, and we're going to replace page 3, which is the farthest from page 2. Okay, 3 will be replaced. Okay, so there's a page fault. And then next one, page 3, which is not in the physical memory, so we're going to replace it, right? So then again, 2 was referenced, so we don't replace 2. 1 was recently referenced, don't replace 1. And 0, don't replace 0. So we're going to replace what? Replace 4, right? So there's a page fault. Then there's no page fault because 0 is in the physical memory. So 0, 1, 3, 2. Okay. Now the implementation for the LRU is also pretty simple. So what we're going to do is we're going to use a queue. The size of the queue is the size of the physical memory. Okay. So in this case, we have 4 frames. So the queue size is going to be 4. Now at the queue head, that's the bottom. The bottom one contains the page that has not been referenced for the longest time. And the next one is 1. Next one is 2 and the 3. So we assume that the page 0 was loaded into memory, the oldest one, then followed by 1, 2. So that's why the order is just opposite. The queue head contains 0 and the 3 was recently referenced. Most recently referenced. Now using the LRU, let's see, we have to keep updating the queue. Okay, We have to keep updating the reference queue. So even though the first reference is page 2, and the page 2 is in the memory, so there's no page fault, but still this changes the reference order in the queue, because now 3 is no longer the most recently referenced page. 2 is, so we have to put the 2 at the top and push the other pages down. Push 3 down, push 1. Okay. So then the next page reference 0, even though there's no page fault, but since we actually 0 is referenced, so the most recent referenced actual page is 0 now. So 0 is going to be on the top. And then we're going to push 2 down, push 3, push 1, right? And then again, page reference 3, so 3 going to be on the top now. And then 0, 2, 1. Again, reference 1, so 1 going to be on the top, so it's 1, 3, 0, 2. And now when it comes to page 4, 4 is not in the physical memory, so we have to replace one of the page in the memory, right? Yeah, in the memory. So which one we're going to replace? So 4 is referenced, right? So we're going to put 4 on the top in the queue. Push 1 down, push 3 down, push 0 down, and 2 is actually pushed out. So 2 was has not been referenced for the longest time. Okay. So again, for each page reference, we have to update the queue. Okay. You have to frequently update the queue, even though there's no page fault. So 1 is referenced, so 1 is going to be put on the top. 4, 3, 0. 0 is referenced, so 0 going to be on the top. 1, 4, 3. Now 1 is referenced again. 0, 4, 3. Now we have a page fault, so new page is going to be introduced. So the queue basically contains all the pages which is currently in the memory. But if there's a page replacement, so new page will be replacing the existing page. So 2 going to be on the top now. 2 is referenced. Push everything down, and then push the 3 out. The page 3 out. Again, we have another page fault. So 3 going to be on the top. Push 2 down, push 1 down, push 0 down. 4 will be out. Now in this case, 0 is referenced again. It's even though it's in the physical memory. So then we still update the queue. So in that case, we just reorder the pages in the queue. So that's the LRU. Now the question is, why LRU? Because LRU look at the history of the page reference to make a decision for the future. Okay. Does it work? The answer is, in most cases, it works, and it works very well. Now, what's the logic behind this LRU? Okay. Now, because LRU selects the page that has not been referenced for the longest time. Now, what's the logic behind this? Okay. Now, we assume that so when it comes to the page fault, and we have to replace the page. So which page will be replaced? Which page in the memory will be replaced? And we assume that if that page has been in the memory and has not been referenced for a long time, we should replace that page. Okay. If that page has been in the memory and it was referenced most recently, don't replace that page. Okay. That's the logic. Now, this is actually generally true in our daily life. For example, if you organize the document, okay, so here's a desk. So I have read the document, and I put on the desk, I call the document 1 D1. So saying, okay, I will read the document again. And then I read another document, put on desk on top of D1 and D2. I say, oh, I will, use the document again. I put D3, D4. I put a whole bunch of documents. And so I say, okay, I will actually look at document 3 again. So I just pull the document out, 3 out, and read again. And then put the 3 on top again. So the chance is that if this document is at the bottom and never actually haven't been read for a long time, and most likely I'm not going to read the document in the future. That's a reality. Now, another example is that when you have a party, you join the party and you exchange the business card with people you just met, and you collect all the business card, and once you get home, you just read each of the card and say, oh, this guy is interesting, but I'm not going to call this guy tomorrow. So I put the card back to the pocket, and then I pull out another business card, and I find out, oh, this is an interesting guy. I will call this person tomorrow. And most likely, if you call this person tomorrow, you will contact the person frequently. And if you say you're going to call this guy in the future, not immediately, the chances are you are not going to contact this person. Okay, that's the logic behind the LRU. Thank you.